I mentioned at the beginning of section 6 that hypothesis testing is a continuation of the idea of confidence interval. And I'd like to explain why that is. So, given our last example where we had 64% men to 36% women hired at this company, we rejected the null hypothesis and said that 64% is statistically different than 50%. If we drew a confidence interval around our 64%, what we would find is that our lower bound is 0.052. Sorry. .052 is slightly larger than 0.05. So we would say that 0.5 does not fall within our confidence interval. Well, that's the same thing as saying that 0.5 is statistically different, in this case statistically less, than 0.64. So we can see the connection between the confidence interval and the t-test. The t-score is the number of standard errors that the sample mean is away from the hypothesized mean. The confidence interval emanates from the sample mean. Note that this connection only works for a two-tailed test and is not the same between a one-tailed t-test and the confidence interval. So in calculating the confidence interval, we see that the proportion is 0.064 plus and minus our error term, or most likelihood error, and we get that our lower bound is our sample mean, or 0.64, minus our error, which is 0.1378. And we get a lower confidence interval of 0.502. Now, let's change this problem just a little bit. Let's say that the company states that the proportion of men and women qualified for the job are not the same. In other words, there really isn't an equal number of men and women in the available pool of candidates. So how does this change the problem? Well, the null hypothesis fundamentally changes. See, instead of 0.5 as the hypothesized mean or proportion, we would have to agree that the hypothesized population value is rerun with a new value. So let's argue that there really are 60% men available for this position, not a 50-50 split. So the null hypothesis becomes that the population proportion is 0.6. The alternative hypothesis is that it is not 0.6. If the t-test is significant, then we can compare the sample proportion to the population proportion to see if the true proportion is higher or lower than 0.6. So this is our directionality once again. Now, notice what happens to our t-stat. It drops quite a bit. Well, that's not too surprising because 0.64 would be fewer standard errors above 0.6 than 0.64 would be to 0.5. We would expect that the p-value would climb, and it does, and our t-critical stays the same. So examining the results, since the p-value is greater than alpha, we must retain the null, or sometimes the words are fail to reject the null. We would never use the word prove. Then the proportion of men hired by the company is not significantly different than 0.6. However, this does not prove that it is true. In fact, we only know that we don't have the evidence to prove that it is something other than 0.6. Now let's change it one more time. Let's say that the company shows records that their industry is showing that the proportion of qualified men is actually 70%. So in this case, we hired 64%, but the available pool of candidates were about a 70% or 7 out of 10. We would again change the null hypothesis to reflect this, and we would rerun the test. Well, our t-stat is now negative. However, it is still less than t-critical because we use the absolute value. So the absolute value of negative 0.875 would be 0.875. We compare that to our t-critical two-tailed. We find that it is less. Or we just compare our p-value of 0.38 to our alpha. In this case, 0.386 is higher than the alpha. Once again, we must retain the null. So the proportion of men hired by this company is still not significantly different than 0.7. Now you might question, well, that seems like a different result than the last one where 0.64 was higher than the hypothesized mean. Here, 0.64 is lower than the hypothesized mean. But in statistics, we have to say that they're not statistically different than the hypothesized mean. So let's see how this looks when we shift based on the three different cases. So the original claim was that the pool of candidates were evenly split. In this case, our t-statistic was slightly higher, although it was higher than our t-critical. In this case, we rejected the null hypothesis. When our null hypothesis changed to 0.6, we find that the proportion hired of 0.64 was not statistically more than the expected proportion. And so in this case, we fail to reject, or it should be a T, we retain the null hypothesis. And in the third example, the population proportion is 0.7. We get 0.64, which is less than the hypothesized mean, but it is still not statistically less. So once again, we would still retain the null hypothesis. Now this is where it gets kind of confusing, because in the last two examples, our business decision was the same. We retain the null hypothesis, and this is what's so critical. We recognize that in statistics, and especially inferential statistics, that there will be natural variations, natural randomness in our samples relative to our population. We say that these differences are not statistically significant as long as they fall within the confidence interval. However, as it was with the first example, when our sample falls outside of the confidence interval, then we reject the null and we say that there is a statistical difference between our sample and our hypothesized proportion or hypothesized mean.